This is the Books Podcast presented by Tim Haig.
It's a celebration of not knowing. In structure and behavior, there isn't much difference between protozoa and human beings. Our fundamental thinking about reality, about what's sensible, is not right.
I ask you, gentlemen of the jury, is this the kind of book you'd like your wives and servants to read?
We're a little bit thrilled to have on the Books Podcast Professor Lawrence Krauss, an actual world-famous theoretical physicist. Professor Krauss, thank you very much for joining us.
It's a pleasure to be with you, really, truly.
Your previous books have included, A Universe from Nothing, of which I understood more than I might have expected to. Also, the physics of Star Trek. You reference Star Trek quite a lot in this book, too.
Yeah, well, I think it's nice to try and, if you're trying to communicate with people, it's nice to communicate using things that people are familiar with, and Star Trek is certainly one. I like to connect science and culture, and that was probably my first book that really made that connection strong, and it worked, so why not keep using it?
Absolutely. The present book is called The Known Unknowns, which is to say, let me quote you. Focusing on the edge of knowledge, you write, provides an opportunity to explain how far we've come. So, really, what is the prospect of this book? Is it where we've got to, or is it where we're going? What should we take from it?
Well, it's both, and it's a celebration of not knowing. I mean, I'm not celebrating ignorance. As I say at the very beginning of the book, I don't know are the three most important words in science, but they should also be, in my opinion, the three most important words in society. We'd overcome a lot of problems, including much of the current culture wars, if people just realize that we have a lot to learn from each other and from the universe. Not knowing is an invitation to explore. So, of course, the book is about what we know we don't know about the universe, and that may seem paradoxical, but that's what drives science. The realization of how much yet there is to learn. And it's an opportunity for me, obviously, to use the fundamental questions that people have about the universe as a way to explain how far we've come. But what is interesting, and maybe I hadn't appreciated till I wrote the book, is how the questions that drive science at the forefront today are the very questions that everyone asks about the universe themselves, whether a scientist or not. Are we alone in the universe? What happened before the Big Bang? How did life originate? And all these so fundamental questions. When I see green, is it the same green as you see? So it's kind of interesting that as science progresses, and it's made huge leaps over the last 400 years, nevertheless, the driving questions at the forefront are the ones that everyone has asked themselves. And once again, to return to what you asked at the beginning, to try and relate science to the things that people are comfortable with is incredibly important to me, because science is or should be a vital part of our culture. That's the reason I do what I do.
Quite a lot of what you deal with is fairly counterintuitive as well, though.
Well, yeah, which is great, because also, one of the big problems in academia and other places now is people wanting to feel comfortable and safe. And the whole purpose, I used to say the purpose of education is to make us feel uncomfortable. Because if we're not uncomfortable, then we're not pushing our own limits. And science forces that upon us, because nature, the imagination of nature is far greater than the imagination of humans. And so we're constantly surprised. I often say that every day I'm surprised if I'm not surprised, because it's that observational and experimental aspect of science that's so important. I'm a theoretical physicist, but it's the fact that nature determines what's correct, not what our prejudices or desires are. And that's the wonderful thing about science. It forces that upon us.
You're not that worried about people being comfortable. As another quote is, the universe does not exist to make physicists happy. And that's a theme that you go back to in pretty much every chapter, that, just because something looks pleasing to us or is intellectually satisfying doesn't mean that it's true.
Yeah, absolutely. And again, I think most people should realize that the world doesn't exist to make us happy, whether we're physicists or not. And that should inspire us, I think, as well. Maybe it depresses some people, but and it's something we have to remind ourselves. Scientists, I'll let you in on a secret. Scientists are human beings, and that means they're subject to all of the whims and frailties of humans. And so we are inevitably driven by things that we want to be true, prejudices, etc. And it's the process of science that forces us to confront our own misconceptions. And isn't it lovely? If being wrong is something that's exciting for scientists. It's not something to be embarrassed about because it means you've learned something.
All that said, of course, this is an optimistic book. I mean, the layman might imagine that some of the questions you're asking are not simply unknown, but unknowable. You know, things like, well, you mentioned what happened to the instant of existence. I don't like the word creation for obvious reasons. Or,
right.
you know, whether there are many or infinite numbers of universes, what consciousness actually is. But while the layman might think that these are unknowable, you tend not to see things that way, do you?
Yeah, I don't like the idea. It amazes me when people suggest there are some things that are unknowable. It is true. The human brain, we still don't understand how it works. And there may be fundamental limitations of our understanding based on our structural makeup and the fact we use mathematics to describe the universe. But we haven't encountered any such barriers. Sure, we've encountered local roadblocks, but we've gone around them. And so when people say something's unknowable, it suggests that they know it's unknowable. But how do they know it's unknowable unless they understand it? So when people say we'll never understand love or a certain type of person can never do science, it's these dogmatic statements that are based on no evidence whatsoever. You can't possibly know what we will never know unless you know it. And so we just keep trying. And again, being aware of the things you don't know drives you on. The unknown unknowns are more fascinating, but it would be a much shorter book.
Well, that's true. Well, look, in that case, let's cherry pick a couple of the questions that you have looked at. And you mentioned maths there. Mm-hmm. One of the notes I made as I was reading the book is does maths make the world, or is it adjectival? Is it descriptive of a sort of underlying reality? Is maths the reality?
Yeah, I mean, people ask, did we discover or invent mathematics?
Yeah.
Mathematics happens to be, as far as we can see, the best language of nature. It works. Nature appears to be describable and predictable as a result of mathematics. Mathematics is a product of the human mind. But it clearly gives us a connection to nature that we had no right to expect. I mean, it was one of the things that Einstein was so fascinated about, was that the universe was understandable, was amazing to him. It was the biggest surprise. And I just did an event with my friend Richard Dawkins, and as he might say, it's amazing that whatever evolutionary forces shaped our psychology to avoid predators on the savannah in Africa, that this byproduct of language and mathematics arose. Clearly, it didn't have any. It's hard to imagine any evolutionary advantage at the time that we would have obtained from mathematics now. So we've happened upon a successful language, and mathematics is more than just a language, though. It's a connection. Again, Richard Feynman, who I quote a lot because he's influential.
Well, he was one of the greats. He was a communicator.
He was a
teacher.
I've learned a lot. Yeah, he influenced me in many ways. But he pointed out, I can say, let's take Newton. We're here in England. Newton would say, if gravity, I can describe the force of gravity as by the product of two masses over the square of the distance between them, and that's Newton's law of gravity. But I can also make the statement that the planets go around the sun in ellipses, passing through equal areas in equal times. In English, those are two separate statements. What's amazing is that mathematics shows that those are exactly equivalent. So mathematics gives us connections between two things that seem completely different, that without mathematics we wouldn't understand are different aspects of the same thing. And that's one of the beauties of mathematics and science, that it shows us connections that we could never have anticipated otherwise.
So that it is descriptive, but it's more than
it's predictive. It's descriptive, but it's predictive. And that's the whole point of science. Science isn't just a story. It would be religion if it was just a story. It gives us, it's the predictive power of science that gives it its power, and why it's important, because we can predict the future up to a certain level, and that gives us an ability to do things we couldn't do otherwise.
You associated that with language, with spoken and written language there, which, I mean, skips on all the way to the final chapter, but why not? So, consciousness is one of the big known unknowns. And again, people will often think that it's something that we'll never fathom properly. Obviously, you have this optimism, which I rather like. What I did like very much in the book was your sort of evolutionary story of how consciousness might have been an evolutionary advantage, and why that as it were, emergent phenomenon might have come about.
Well, I mean, again, it's not unique to me. I think I learned it by reading and talking to people who study this for a living. But consciousness it's the last of the 5 sections of my book. It's the last for many reasons, because I think it's the most difficult problem. And I often tell people I'm a physicist because it's easy. And
it might be the hardest problem. I found it the easiest part of the book.
Yeah, no, it's true. It's the most. It's that wonderful irony, because it's the most intuitive. We all are aware of our own consciousness. So in a way, there's an arc. I begin with time, which is again a personal thing, and then we move around and we come back to consciousness, which is, you couldn't be more personal. We have our own consciousness. But the amazing thing about that is we have our own consciousness, and we have no idea. We have this faith that that other people's consciousness are the same thing, but how do I know? And it's that inability to go into the mind of others, except by our conversation and observing behavior, which provides, from a scientific perspective, a fundamental limitation to really understand, what consciousness is. So how could you approach it? Well, the evolutionary approach is a reasonable one, because if we're interested in what makes us human, and I think most of us would say that what makes us human is our consciousness, whatever that is. And again, it's hard to define, but that's what determines our humanity. Then let's look at how we humans differ from other animals, and try and decide what it is about our biology that makes us unique, and maybe that'll give us some insight into that thing we call consciousness.
Other life forms respond to stimuli.
Yeah.
And the question is what we do different in kind or magnitude?
Yeah, and I love Bertrand Russell once said that basically there's not much, I think I quoted, I don't have the exact quote here, fundamentally in structure and behavior there isn't much difference between protozoa and human beings. And what he's talking about is that in behavior you can see single-celled animals and protozoa, and to some extent even more basic life forms, exhibit behavior that you might attribute to consciousness, avoiding danger, avoiding harmful situations, and even possessing some examples of memory in the sense of knowing where to avoid.
Yeah, finding a hostile environment.
And they don't even have neurons, so we know they're not conscious. But so we have to beware, and this is the thing about science, is making presumptions that aren't justified. You have to constantly check to see if you're doing that. We tend to observe behavior and presume consciousness.
There's a danger of going down the behaviorist route there.
Well,
which
absolutely.
I hope is unfashionable these days.
Well, it used to be fashionable, but it's more than just pure behaviorism. The problem is there's a danger in observing behavior, but what other observable is there? You see, that's the problem. We know that behavior is not always, it's not akin to consciousness, but if we're trying to observe, and as a scientist, so we can understand it, we don't have much choice except to observe either behavior or to question people. But as I show in the book, questioning people doesn't give you that good better.
Except insofar as, in the same way as the infinite universe question crops up, we do have one consciousness, one sense of self that we're intimately familiar with. So, I mean, yes, you have the problem of inferring other minds, but it's not simply a question. It's only a question of observing behavior for other selves, isn't it?
Yeah, but what I show in the book is we're not even aware of our own consciousness. The split brain experiment, which I love describing in the book of Michael Gazzaniga and others, shows that when even you think you understand what it is you're experiencing, that can be an illusion. But First of all, it's not operationally very significant for me to say that. It may be an illusion, but if I kick you in the shins or you're jilted by a lover or something yourself, it's really important. But more importantly, the question is, how does that illusion arise? That's what we want to understand as scientists. The same as at the beginning of my book, some people say time is an illusion. How does a sense of time? So saying it's an illusion doesn't add much. Life is an illusion. As a physicist, I know the classical world I experience is just a mask of an underlying quantum mechanical universe that's far stranger. Well, fine, okay, but how does that classical world result? How does that amazing illusion result? So accepting that the life we experience in some sense is an illusion doesn't mean there's no underlying reality and that, everything's subjective. It just is a reflection of the amazing, fortunate experience we have of being conscious in a strange and wonderful world.
You have a reputation for being a bit impatient with philosophers. You say in your book that if philosophers have anything useful to contribute to these kinds of questions, it's because the science is in its infancy.
Well,
I
don't use it as pejorative. Yeah, so people claim I give, it's like, philosophy a bad rap. And I think because I've made some jokes, but we all do philosophy. Philosophy is discipline. My friend Anthony Grayling, who I was just with, he would say philosophy is sort of disciplined critical thinking, and I agree with that. And that's the basis of science. But philosophy is a discipline which is really designed to think of good questions. Okay, and the areas where it can contribute to science are the areas where we don't know what the good questions are. So they tend to be most useful in the infancy of science, useful in the beginning of physics. Okay, but now the professional area of philosophy, and this is a fact, it's not a pejorative statement, but it's just a fact, it has very little impact on physics. It's not saying the philosophy of science or the philosophy of physics is unimportant, it just doesn't affect what physicists do.
Whereas if you go back to the ancient Greeks, it was the same thing.
Yeah, or even Newton, or Galileo, those philosophical questions were important, but physics has progressed, so the questions we come up with are not determined by philosophers, okay? But the areas of science that are still in their infancy, like our understanding of consciousness, are areas where philosophers can really contribute because we don't know what the good questions are. And so you see in that area equal contributions right now between what you might call professional scientists, neuroscientists, or cognitive scientists, and philosophers. And I quote both, I quote both because they're useful, and maybe it'll also convince people that I don't despise philosophy.
Can I take another dive in?
Sure.
One of the things that interests me and which really bothers me about your field of knowledge is infinity.
It should bother you, by the way.
One of the best quotes in the book, which is full of really quotable stuff, is you say infinity is different from just very big. I read that book of Carlo Rovelli's, which was called "The Universe Is Not What It Seems," in which he's proposing a quantum loop reality, which I don't think you're terribly taking.
I don't find it particularly useful, but anyway.
We come back to your point that it's not there to make physicists or indeed laymen happy.
Yeah.
The reason that appealed to me is that it suggested that at the tiniest level, the Planck level, that space is not continuous. It's granular, discontinuous. And that, it seemed to me, might sort of remove the necessity or the tendency to infinities in the universe. And I found that comforting.
Well, it's, by the way, just so you know, string theory does the same thing, although it never makes that claim. There really is a smallest distance scale to some extent in string theory. But infinity bothers... It bothers physicists more than mathematicians, but it's I think I use one of my favorite Woody Allen quotes, which is, "Eternity is a long time, especially near the end." If you want to get a sense of how, not in this book, but in other books, I don't think in this book I quoted Hilbert's Hotel, but
yes, you did.
Okay, good. Infinity is fundamentally different and it's strange and crazy. And I'm happy to give the Hilbert's Hotel example if you want, but you can, once you do things with infinite quantities that don't make sense with finite quantities. So physicists, in some sense, especially at the forefront of this kind of science, and in the nature of black holes, the beginning of time, Big Bang, are confronting infinities, and they don't seem physical. And part of the success of physics is to get rid of infinities, is to get rid of infinite quantities. It was a problem in quantum mechanics and quantum field theory that Richard Feynman won the Nobel Prize for, among others, is that the mathematics appeared to give infinite results, which are, as far as we can tell, nonsensical. And getting rid of those infinities and making sense of them, of the underlying physics, is a great success. And we ultimately think maybe if we have a quantum theory of gravity, whether it's loop quantum gravity or string theory or something else, it will get rid of the infinities. Because the problem, we have these two great theories: general relativity, a theory of space and time; quantum mechanics, a theory of how things work at fundamental scales. But when you put them together, they don't mesh. They produce infinite, nonsensical results. And the presumption is that's because we're doing something wrong. And we have to change. Whenever there's a paradox like that, whenever there's a apparent brick wall, it's an invitation, once again, to say maybe we need a new way of thinking. And I don't know whether any of the present ways, if history is any guide, all of our current theories are wrong about that fundamental level, because if they were all right, physics would be trivial. So maybe I'm willing to suspect that string theory has something closer to say to reality than loop quantum gravity, but it's just a personal suspicion. But ultimately, it's, if you take general relativity and you take back to the beginning of time, all of space was at a single point and it was infinitely dense, and that just seems, from a physical perspective, implausible at best. And so
Although
we think
the universe isn't supposed to make you
exactly, and maybe it was, and some people suspect that maybe what we have to give up is this notion of quantum mechanics, where the
Except
infinities rise.
quantum mechanics works on
It
so
works.
many levels.
Well, so does Newtonian mechanics. If you want to, Newton's laws are perfectly useful for cannonballs, baseballs, and even local rocket ships. But we know they have to be modified at some
for
fundamental
GPS.
scale.
Yeah,
and so maybe general relativity absolutely works at the scales where it applies. But that's true for all physical theories. There's no physical theory that is absolutely true, that applies on all scales, as far as we know. Our best theory, called quantum electrodynamics, which Feynman helped develop, it allows us to predict quantities and compare them with experiment to 13 or 14 decimal places based on fundamental science. There's nowhere else you can do that in science. But even that theory has a limited domain of applicability. And so maybe there are a few well-known physicists, like Gerard 't Hooft, who's a Dutch physicist who won the Nobel Prize and produced incredibly important results in particle physics. I know that he thinks at some fundamental scale that when it comes to general relativity and quantum mechanics, what we might have to give up at a fundamental scale is quantum mechanics. Maybe this crazy world, the quantum mechanical world, is indeed just a surface layer of something that may be less weird or maybe weirder. And he's been thinking about it. Now, he may be wrong, but he has a good track record, and at least it's good that some people are questioning that. At the same time, since I brought up quantum mechanics, I'll make a little digression there, because I talk about quantum mechanics in the book because I think so many people abuse it, including scientists who write whole books about the classical interpretation of quantum mechanics, many worlds, and I think it makes them sound good, but that's exactly the wrong way to think about it. The world we live in, which is a classical world, is an illusion. The fundamental world is quantum mechanics. So why should we try and explain the quantum mechanical world in terms of the classical one? We should instead try to understand how the classical world arises from quantum mechanics. We don't try and explain curved space-time in terms of Newton's laws. If we did, it would come up with a ridiculous, it would seem weird. We have to understand that space is curved. Well, we have to understand the world is quantum mechanical, and there are experiments I do, and I talk about in the book, that show our fundamental thinking about reality, about what's sensible, is not right, like it or not. And anytime we try and explain the quantum world in terms of the classical world, we're going to come up with weird things, spooky action at a distance, as Einstein called it, and that you may not like it, but once again, I don't care if you like it.
It seems to happen.
It not only seems to happen, but that spooky action at a distance is only spooky because you're thinking about it wrong. Yeah. If you think about it from a quantum mechanical perspective, purely quantum mechanically, that spookiness kind of disappears. It's only a product of the fact that we appear to be classical beings. And so the spookiness comes from the fact that we happen to have an illusion of reality that is just an illusion.
You mentioned many worlds there, and in the book you suggest that while a multiverse, if there was one, it would be necessarily inaccessible to us by definition.
Yeah.
You do suggest we might be able to infer it.
Yeah.
From what?
And it's, by the way, let me make it clear, that kind of multiverse is different than the many worlds of quantum mechanics.
Okay.
And to refer to Star Trek or other examples, the many worlds of quantum mechanics suggest each time I make a measurement, I'm choosing one reality, and there are an infinite number of other ones that branch out. And it's a great fodder for science fiction because you imagine, the bad Kirk coming from, some other quantum. And the whole point of quantum mechanics is that picture is only a reasonable interpretation if you always stay on one branch. You can never jump between branches. So those other worlds are really imaginary other worlds. But it could be that there really are other worlds. In fact, the current consensus, I would say, in cosmology is that our universe is part of a multiverse, that there are other universes that are forever removed from us in distance, and the distance is growing, so we can never measure them directly. And what amazes me, and you alluded to, that sounds like metaphysics, which sounds like philosophy, but in fact, you can make it science because we can never detect those other worlds directly, but we could do experiments which indirectly tell us that they might exist. And I have written papers that show that if somehow we could measure something called gravitational waves from the early universe, it would allow us to, in principle, infer that those other worlds have to exist. Those other multiverses have to exist. And that may not seem satisfying, but the example I use is the example of atoms. 100 years ago, a little over 100 years ago, say 1905, chemists had been using the idea of atoms for a long time, but many of them still thought the idea was a mathematical construct that was useful, but atoms weren't real physical things. Einstein, in his 1905 PhD thesis, it was a good year for him, showed a way to determine the reality of atoms, if you wish. And it wasn't just through him, but within 5 years, everyone accepted reality of atoms, even though, and I remember as a student being told, you can never see atoms directly. Light, and you can't. Light can't detect atoms. Atoms are smaller than visible light, so we used to think you'd never be able to detect them directly, but we all inferred their existence, and no one doubted the existence of atoms. Well, it turns out we can detect atoms directly now and see them in a generalized sense. But no one was bothered by the fact that you could never see atoms directly, but you could infer their existence. And it may be that in the future, we will be able to infer the existence of those other universes, even though we'll not be able to detect them directly. And that scientific inference will turn metaphysics into physics, which is always a good direction as far as I'm concerned.
Shall we take one more paddle in the shallow end here?
Okay.
Section 4 is life.
Yeah.
So the big question is life on Earth unique? And by extension, is there life elsewhere in the universe? And if there is all life the same everywhere?
It is fascinating because that is one of the questions that everyone asks, and so, the book begins time, space, matter, and then life. And interestingly, it again is immediate. We all wonder, when you look up at the stars at night, are we alone in the universe? But we do have to ask questions like, what is life? And it's amazing when you ask yourself that question, how...
It's hard to get a definition, isn't it?
Yeah, you think it should be obvious.
Yeah.
Like consciousness, and I think I quoted Justice Sewell, the famous example of pornography, saying, I don't know what it is, but I know it when I see it. And that's how many people feel about consciousness and life. Because I give the example of fire. Fire, so if you think of life as something that reproduces, that has a metabolism, that
consumes,
and so in many ways, fire has all of those things, but I think very few people.
But it's not self-regulating.
That's the key point. So you have to want to add homeostasis.
Yeah,
that it's self-regulating, and that's a really important part of life, and that's relevant, by the way, for consciousness, as I talk about in the later chapters. But the self-regulating aspect is what's so surprising. One of the many non-intuitive aspects. Life appears, for many people, to violate what they would think would violate the laws of physics. And Erwin Schrödinger, when he wrote his book, What is Life?, which was incredibly influential. So Erwin Schrödinger, who helped develop quantum mechanics, later on in his life wrote a book called What is Life in 1946. Jim Watson who wanted to be wanted to study birds, ornithologists, read it and got interested in what eventually became genetics, and of course was one of the discoverers of DNA as a result of it. This question of, well, when we look at the world around us, entropy, the world becomes more disordered. But life is clearly an example of disorder becoming ordered. The fact that we constantly battle entropy. And for some creationists, that they think it violates the second law of thermodynamics. It doesn't.
But they don't know what they're talking
Exactly. They don't know what they're talking
In
about.
fact, that was almost one of my questions. Is it worth demolishing the arguments of creationists? Or
Well,
should they
sometimes
just be
it is.
shoved
Well,
to one side?
it's not. I don't believe in giving people airplay when they don't need it, or or giving them advertising. But I think a lot of people do wonder about how amazing it is that life seems different than everything else we see, and therefore many people are suspicious that there is something divine about life, and I just want to show that that's not necessary. The life is not different than snowflakes. Snowflakes are beautiful, ordered systems that occur, and they occur naturally just because of the laws of polar molecules in chemistry and physics. And so, but what bothered Schrödinger enough that he talked about it in his book, and the important thing is that talking about it influenced a whole generation of scientists who began to explore the genetics of life. And part of the problem when we think about are we alone in the universe is the fact that we have one example of life. I quote Schrödinger later on in the consciousness chapter with a beautiful quote saying something like, consciousness is a singular of which we don't understand the plural. The same is true for life. We know of one example of life. So when we look at the universe, scientists are always like drunks coming out of a bar and who lose their keys. Where do they look for their keys? Under the lamppost. Why? Not because it's where they lost it, but it's where they can see things. So the first presumption we look out at life in the universe, try and find is maybe it's life like us.
Yeah, but your optimism leads you to make another excellent point, which is that life began on Earth more or less as soon as the physics allowed.
Yeah.
And you sort of extrapolate from that to suggest that maybe that's reason to hope that there is life elsewhere in the universe.
Yeah, no, and it is a empirical fact that life, the laws of physics would not have allowed life to have arisen much earlier than it did on Earth, and amazingly quickly it developed. And so, of course, that's one example. Maybe we're a remarkable exception, but the simplest assumption is that in some sense we're typical, and we may be wrong about that. And if life arose so easily on Earth, then presumably it can arise easily with what do we know is a prerequisite for life on Earth? Well, energy, light from the sun, water seems to have been essential, and organic molecules. But all of those exist. We observe organic molecules in comets, in interstellar space. Water is everywhere. Sunlight is everywhere. So, maybe in the oceans of Enceladus, there are the similar conditions. And so it gives reason for hope. Hope, as I point out, is not evidence that it exists. And so we have to go out and search. But now what's amazing is we have the mechanisms, we have the new tools that actually we've discovered planets around, thousands of planets around other stars. We know of the existence of organic molecules in our environment and in other comets. And we now have tools that allow us in principle to explore the atmospheres of other planets, if we can discover such atmospheres, which we haven't done yet. And that opens up a whole new window on the universe. Every time we open up a new window on the universe, we've been surprised. And so maybe we'll be surprised to find we're alone, in which case Carl Sagan's statement that, it seems like an awful waste of space if we're alone in the universe. Or maybe we'll be surprised, as we've been surprised when we discover other solar systems. We used to think our solar system was typical, with giant gas outer planets and rocky inner planets. And now we've discovered that we may not be typical at all. There are lots of solar systems with giant gas planets quite near their sun. And so we have to learn once again that our presumptions of what seems natural may not be natural. And we may be surprised, and I suspect that one of the biggest surprises will be where life can exist. We've been surprised on Earth. Once again, the discovery of what are called extremophiles. Well, you used to assume, well, if, life would exist in nice environments like the ocean, but life exists in acid environments, and there are life forms that only can exist in boiling acid environments, which you'd imagine would kill anything. Life also, this is another reason for optimism, life seems to be able to survive and exist in almost every environment in which it's physically possible. And that gives hope because the universe has very many, many environments. And so I guess it's one of the areas where I am optimistic.
Actually, that brings me to my last couple of questions.
Sure.
One of which is, of all the questions that you raise in your book, which are you most optimistic of getting answers to in your lifetime?
Yep.
And if you want to extrapolate, my 18-year-old daughter is about to do physics at university. You can do her lifetime as well.
Good choice for her. But you're right. It was a good segue because I do think among all the questions in my book, perhaps the one which will be solved even in my lifetime, or at least where we'll have great new insights, is life. Because from the double-ended parts of it. First of all, as I just mentioned, we have a whole new set of tools. Whenever there's a whole new set of observational tools, science progresses at an incredible rate. We now have astrophysically can observe parts of the universe we never thought we'd see before with the James Webb Space Telescope and
Which
other
is
things.
wonderful.
Yeah, well, unbelievably great. So that gives us a new handle. We also have the tools to explore robotically, not with humans, but robotically, the solar system, places we could never go with humans, like the oceans of not never. Never is a long time, But it's very difficult to imagine that we would send humans productively to Enceladus, drill down through a kilometer of ice and explore the oceans, but certainly robotic systems can. But at the same token, we're also proceeding to understand life on Earth. It's hard to imagine that we can productively explore life in the universe without understanding the origin of life here on Earth. And some amazing surprises have taken place in understanding how complex things like RNA might develop. That's one of the biggest paradoxes. Even at its simplest form, life is incredibly complex, which is one of the things that's pushed creationists as well. Even at its simplest form, even in an RNA world, which might have preceded a DNA world, RNA is a complex polymer. Well, when normally complex systems break down, but what's been discovered is in unique environments, like maybe on an asteroid, where there's lots of ultraviolet light and lots of energy, you can actually find chemistry goes in the opposite direction of your intuition. And simple molecules can naturally form complex systems. That's an amazingly important discovery. And I think I think in my lifetime it's possible that we'll have found a plausible route, if not be able to prove that it is the route, by which chemistry becomes biology. I mean, that's the biggest mystery. How did chemical systems, prebiotic systems, suddenly become self-replicating, self-regulating systems with a membrane and all the things that makes life seem unique? And I think that we may have the answer to that. And if we do have the answer to that on Earth, it will give us a real handle to tell us where to look for possible life elsewhere. So, yeah, for me, I'm most optimistic that in my lifetime we'll answer that question. But the great thing is, you never know. And the deepest mysteries may be just around the corner to answer. And that's why, I wrote my book, I say at the end of my book, that when I was a student, I read a book by Richard Feynman called The Character of Physical Law that a teacher gave me when they saw I was bored with what was going on. And what amazed me about that was it was the first time that I saw that it hadn't all been done before. I loved science, but I loved Einstein and all. But it seemed to me like all the big questions had been answered. When I suddenly discovered that they hadn't been, that was an invitation to me to become a scientist. And my great hope, although it may not be an expectation, it's a hope, is that some young person will read my book and read about those unknown unknowns and become a scientist and answer some of those questions.
This is going to be slightly cheeky of me. What sort of a shelf life do you think your book is going to have? In how many years might physicists say, "Oh, yeah, I got that one"?
Well, I said at the beginning, another book that inspired me was, and in fact inspired my publisher here, who was reminding me of it, was The Mysterious Universe by Sir James Jeans, which was a 1930s bestseller, I think. And it's a very quaint book to read now, because what he thought was, mysterious about the universe in 1930, some of the questions aren't even the reasonable questions anymore. My hope is that within a generation, my book seems quaint. It's even more than a hope. It's a full expectation. Science progresses. The questions I point out here may not even seem like the real questions. So the quicker my book becomes, in a sense, outdated, the better. And I don't mind that. In fact, I think it will be a testament to science to see how quickly I can be wrong. And it doesn't bother me at all.
Well, it doesn't bother me either, because for the moment, the book is bang up to date. And as you can tell, I enjoyed it enormously.
Thank you.
So thank you very much. The Known Unknowns by Lawrence Krauss. It's published by Head of Zeus at £20, and I'm going to go and read it again.
Thank you very much, and
Thank
I
you
hope
very
I hope it inspires, and if it confuses a little bit or upsets, that's maybe even better.
That was Books Podcast, presented by Tim Haig. Books Podcast is a Green Shoot production. You can find out more at www.green-shoot.com, and Tim can be contacted on tim@green-shoot.com.